You have a sorted collection of data, and you need to find one element. If it's in an array, you can use binary search, jump to the middle, compare, and cut the search space in half each time. That's O of log and fast and elegant. But what if your data is in a linked list? Now you're stuck. You start at the head and walk forward one node at a time. There's no way to jump to the middle. No shortcut. Every search is O of n. Here's the thing though, linked lists have their own advantage. Insertions and deletions are O of 1 if you already have a pointer. Arrays need to shift everything over. So you're caught in a trade-off. Fast search or fast modification. Pick one. But what if you didn't have to choose? What if a simple coin flip could give a linked list the same search performance as binary search? In 1990, a computer scientist named William Pugh invented exactly that. He called it the skip list. Let's start with what we know. Here's a sorted linked list. The head points to 3, which points to 7, then 12, 19, 22, 25, 31, 38, 44, 50, and finally 55. Every node points to the next one in sorted order. Now let's search for the value 44. We begin at the head. Is it 3? No, move forward. Is it 7? Number 12. No, we just keep walking. 19, 22, 25, 31, 38. 9 comparisons later, we finally find 44. And this is a small list. Imagine a list with 1,000,000 elements. Searching for something near the end means visiting nearly every single node. The fundamental problem is that a linked list gives us no mechanism to skip ahead. Each node only knows about its immediate neighbor. We have no global view of the data. We can't binary search because we can't index into the middle. We're forced to traverse linearly. But what if some nodes had extra pointers that let us leap forward? Here's the idea that changes everything. What if some nodes had an extra pointer, an express lane, that skips over several nodes at once? Think of it like a subway system. The local train stops at every station. The express train skips stations, covering more ground with each stop. If you need to get somewhere far away, you take the express train first, then switch to the local train for the last few stops. Let's apply this to our linked list. We'll add a second level of pointers. On this express level, we connect every other node. So the express lane goes 3, 12, 22, 31, 44, and 55. Now let's search for 44 again. We start on the express level. 3, 12, 22, 31, the next express stop is 44. Found it directly on the express level, just 5 comparisons instead of 9. Even when the express lane doesn't land exactly on our target, it gets us close. Then we drop to the local level and walk a few steps. We've already cut our search nearly in half, but we can do much better. If one express lane helps, why not add more? Let's stack additional levels on top. Level 0, the base level, has every node. Level 1 connects every second node. Level 2 connects every fourth node. And level 3 connects every 8th node. See the pattern? Each level has roughly half the nodes of the level below it. Level 0 has n nodes. Level 1 has n over 2. Level 2 has n over 4. Level 3 has n over 8. This is starting to look a lot like binary search. At each level, we skip over large chunks of the list. The top level gives us a bird's eye view. Each level down zooms in further until we find our exact target at the bottom. With log n levels, the total number of comparisons becomes O of log n. We've turned a linear time linked list into a logarithmic time search structure. But there's a catch. If we rigidly assign every second node to level 1 and every fourth to level 2, then inserting a new element would force us to restructure all the levels. That's expensive and complicated. We need a smarter approach. Let's nail down exactly how search works in a skip list. The algorithm is surprisingly simple. Start at the top left corner, the head node at the highest level. Now follow 2 rules. Rule 1, look at the next node on your current level. If its value is less than or equal to your target, move right. Rule 2, if the next node is greater than your target or there is no next node, drop down 1 level. Repeat until you either find the target or reach the bottom level with nowhere else to go. Let's trace a search for the value 38. Starting at level 3, the head's next node is 25. That's less than 38, so we move right to 25. From 25 on level 3, the next would be past our range, so we drop to level 2. From 25 on level 2, the next is 31. Less than 38, move right. From 31, the next is 44. That's greater than 38, so drop to level 1. From 31 on level 1, the next is 38. Found it. 5 comparisons across 4 levels. The search zigzags down through the levels, narrowing the search window at each step. Here's where skip lists become truly brilliant. The question is, when we insert a new node, how do we decide which levels it appears on? The deterministic approach, every second node on level 1, every fourth on level 2, requires expensive restructuring. William Pugh's insight was stunning in its simplicity. Just flip a coin. When you insert a new node, you always place it on level 0. Then flip a coin. Heads, promote it to level 1. Flip again. Heads, level 2. Keep flipping until you get tails. That's it. That's the whole level assignment algorithm. On average, 1 in 2 nodes reaches level 1. 1 in 4 reaches level 2. 1 in 8 reaches level 3. This geometric distribution is exactly what we want, roughly half the nodes at each successive level. Some nodes get lucky and climb very high. Others stay at the bottom, and that's completely fine. On average, the structure looks just like our idealized version with perfectly spaced levels. This is the genius of skip lists. Randomness replaces complex rebalancing. No rotations, no color flipping, no balance factors, just a coin flip. Let's walk through a full insertion. We want to insert the value 27 into our skip list. First, we flip coins to decide the level. Heads, heads, tails. So node 27 will appear on levels 0, 1, and 2. Now we need to find the right position for 27 at each level. We search just like before, starting from the top. But this time, as we traverse, we record the last node we visited at each level before dropping down. These are called our update pointers. At level 2, we pass through 25. That's our update pointer for level 2. We drop down. At level 1, the update pointer is also 25. At level 0, same thing, 25 is the last node before where 27 belongs. Now comes the pointer surgery. At each level, we splice 27 into the chain. Node 27's forward pointer gets whatever 25 was pointing to. Then 25 points to 27. We do this at levels 0, 1, and 2. The old chain is preserved perfectly. We just inserted 27 into exactly the right position at every level. No rebalancing, no rotations, just simple, local pointer updates. If insertion is simple, deletion is even simpler. To delete a node, we first search for it, just like a normal search. But as we traverse, we record the update pointers at each level. These are the nodes that currently point to our target. Let's delete node 27 from our skip list. We search from the top and find it appears on levels 0, 1, and 2. At each of those levels, we know which node points to 27. Now we bypass. At each level, the update node's forward pointer skips over 27 and points to whatever 27 was pointing to. The chain reconnects as if 27 was never there. One small cleanup step. If removing the node empties the highest level entirely, we reduce the skip list's maximum level. This keeps the structure tidy. And that's it. No cascading fixes, no restructuring. Compare this to a red-black tree, where deleting a node can trigger multiple rotations and recolorings to maintain balance invariance. With a skip list, deletion is always just local pointer updates. Clean, predictable, and fast. Let's prove why this randomized structure actually gives us O of log n performance. Each node is promoted to the next level with probability 1/2. So the expected number of nodes at level k is n over 2 to the k. The highest occupied level is where n over 2 to the k equals 1, which gives us k equals log base 2 of n, so the expected height of the skip list is O of log n. Now for search cost. Consider the search path backwards, from the found node back to the top left corner. At each step, we either go left or go up. Going up happens with probability 1/2. The expected number of steps at each level is constant. With O of log n levels, the expected total search time is O of log n. What about space? Each node has, on average, 2 forward pointers, one for level 0, and the geometric series 1/2 plus 1/4 plus 1/8 sums to 1 more. So total space is just O of n. The theoretical worst case is O of n if every coin flip lands heads, but the probability of this is vanishingly small. In practice, skip list performance is remarkably consistent and tightly concentrated around the expected O of log n. Skip lists aren't just a theoretical curiosity. They power some of the most important systems in production today. Redis, one of the world's most popular in-memory databases, uses skip lists for its sorted set data type. Every time you run a zadd or zrange command, you're using a skip list under the hood. LevelDB and RocksDB, the storage engines behind countless databases and applications, use skip lists for their in-memory write buffers, called memtables. And Java's standard library includes ConcurrentSkipListMap for thread-safe, sorted data. So why would these systems choose skip lists over balanced binary search trees? First, skip lists are dramatically simpler to implement. No rotation logic, no color flipping, no balance factors. The entire implementation fits in a fraction of the code a red-black tree requires. Second, skip lists are naturally suited for concurrent access. Lock-free skip list algorithms exist because each level can be updated independently. Balanced trees require locking entire subtrees during rotations. The trade-off is that skip lists use slightly more memory, and their performance is expected O of log n, not worst-case guaranteed. But in practice, the variance is tiny. William Pugh's 1990 invention remains one of the most elegant ideas in computer science. Simple, fast, and beautiful.